Hi friends, today we will try to understand how capacitor behaves when I connect it with the supply. Okay, so basically what will be the current through capacitor, what will be the voltage across capacitor with respect to time. Okay, as time goes, what will be the voltage across capacitor, how we get the characteristics of voltage across capacitor with respect to time, what will be the current through capacitor with respect to time, what will be the equation for that, and how the charging and charging voltage, or we can say the voltage across capacitor builds up, current through capacitor builds up. Okay, that we will see today with one example of two tank analogy of two water tank analogy. Hope you will enjoy it. Okay, so we'll start with this. So what happen when the capacitor is connected to certain supply? For example, I am connecting the capacitor with DC supply. Okay, there is one switch. Okay, and let's say there is one resistor is connected and there is one capacitor. Okay, so what will happen, let's say this is R and this is capacitor C. Okay, this is DC supply. Now we'll try to understand this with the help of two tank analogy. For example, there are two water tanks. Okay, say this is tank number 1 and this is tank number 2. Both water tank are connected with pipe and there is one cock over here. Say this is C is the cock. Okay, consider this water tank is full with the water, with the liquid. Okay, and this is a constant, this water, the level of the water will remain constant. For example, okay, consider the water level in this tank will remain constant up to this level. Okay, now what will happen, initially this tank is totally empty. Okay, now whenever I will open this cock, what will happen, the water will starts to flow from this tank to this tank with very high velocity of water through this pipe. Okay, so large amount of water will starts to flow from this tank to this tank, and the water level in this tank will be rises. Okay, gradually the water level will be rises. Now up to what level this water will rises? Up to this level, because we have considered that this particular tank has a constant level of a water. Okay, so gradually the water level will increases up to this level. Okay, after that there is no difference of the potential of a water, so water will not flow from this tank to this. Okay, so initially with large velocity water from this pipe will flow to this tank. As this level of water increases, this flow, the flow of this water, or the velocity of flow this water will gradually reduces. Okay, as the level of water increases in this tank. Okay, so using the same concept, we'll try to understand what will be the voltage across capacitor and current through capacitor with respect to time. Okay, so now consider, initially the valve was open. So now consider in this circuit, initially the switch is open. Okay, so the valve is open, so there is no flow of current through this valve or through this pipe. Okay, as the switch is open, there is no flow of current through this circuit. Okay, so initially there is no flow of current. Now whenever I open this valve, large amount current will flow. Okay, and this tank is totally empty. Okay, similarly whenever I close this switch, let's say I am closing this switch, it's at t is equal to 0 time. Okay, so just like this second tank is totally empty, so this capacitor is totally discharged. This capacitor does not have any voltage initially. Okay, so I can put this point here, at t is equal to 0, the voltage across capacitor is 0. Okay, and as the switch is closed, here large amount of water will flow with high velocity. Similarly, when this switch is closed, large amount of current will flow through this, because this has a zero voltage and this has a max VDC voltage. So there is a maximum potential difference, so large amount of current will flow. So the current will be maximum initially whenever I close this switch. Okay, and as this tank, the water level in this tank gradually increases. Okay, so we can say that the voltage across capacitor will gradually increases. Okay, up to what level? Up to level of voltage which is same as VDC. Okay, just like this, the water level will increases up to the level of the first tank. Similarly, the voltage across capacitor will be, final voltage will be same as the voltage of the battery. So this voltage will gradually will increase like this. Okay, now what about the current? Initially, the current through this valve, whenever I open this valve, the current through the water through this pipe has very high velocity. Okay, and as this water tank gradually filled up, this velocity will reduces. Similarly, when at t is equal to 0, I close this switch, large amount of current will flow. Okay, and as the voltage across this capacitor will builds up, this current will gradually reduces. So current will be gradually reduces like this. Okay, so this is voltage versus time and current versus time characteristics of capacitor. Okay, now what about the equation? Okay, so voltage across capacitor, if I want to write, say, voltage across capacitor with respect to time, v of t. Okay, so that will be equal to v0 into 1 minus e raised to minus t divided by RC. Okay, RC is the time constant, as I have connected R and C. Okay, now if I solve this, so that will become v0. If I multiply with this, v0 minus v0 into e raised to minus t divided by RC. Okay, now if I put t is equal to 0 here, so anything raised to 0 is 1. So v0 minus v0, that is equal to 0. So at V, voltage across capacitor, say this is voltage across capacitor, at t is equal to 0. Okay, so I put the value of t is equal to 0 in this equation, that will become v0 minus v0, that is equal to 0. Okay, so I can show it like this. Okay, and finally I put, this is for t is equal to 0. Now at t is equal to infinite, what will happen? So at t is equal to infinite, e raised to minus infinite is 0. So voltage across capacitor at t is equal to infinite will be v0 minus 0, that is equal to v0. So v0 is nothing but the voltage that we have applied. So at finally at t is equal to infinite, at t is equal to infinite, if the voltage across capacitor will be v0. Okay, why? Because when I put t is equal to infinite over here, e raised to minus infinite is 0. So v0 minus 0, so that will be equal to v0 at t is equal to infinite. At t is equal to 0, I put t is equal to 0, so e raised to 0 is 1. So v0 minus v0, that will become 0. Okay, so from this we can say that t is equal to 0, vc is 0. At t is equal to infinite, vc will be equal to v0, so that is equal to v0. Okay, now what is the current through the capacitor? Okay, so I say IC of t is equal to I0 e raised to minus t divided by RC. Similarly, I put, say, t is equal to 0. So at t is equal to 0, IC of 0, okay, current through capacitor at 0 will be equal to what? I0 into e raised to 0, that is equal to 1. So that is I0. So that is maximum current. And at t is equal to infinite, so at maximum time, IC is infinite, so I0 into e raised to minus infinite, e raised to minus infinite 0, so that will become 0. Okay, so we can say that at t is equal to 0, current through capacitor will be I0, that is equal to maximum. Okay, and at t is equal to infinite, okay, if I put the value in this, so ICT will be equal to e raised to minus infinite, that is equal to 0. So at t is equal to infinite, this current will become 0. Okay, so this is how the voltage through voltage across capacitor and current through capacitor behaves with respect to time. This concept is very useful whenever we use RC tank circuit, LC tank circuit, RLC series circuit, RLC parallel circuit. Okay, and this RC is known as a time constant. Okay, it is also written as tau, and it is the time constant of this circuit. Okay, time constant of this circuit, and this is very useful whenever we are solving, or we analyze the circuit at particular time. Say t is equal to 5 microsecond, what will be the voltage across capacitor? At t is equal to say 6 microsecond, what will be the current through the capacitor? Okay, so that kind of analysis we can do with this equation. So these two equations are very useful for that. Thank you.